Analysis of a slab floor. An example of a slab floor with girders is selected to illustrate some features of ELPLA for analyzing slab floors. The slab floor has a thickness of 10 cm and carries uniform loads with different intensities. All girders have the same dimension of 15 cm by 60 cm. Owen weight of the girder may be taken as 1.875 kN per meter. Young's modulus of concrete is 3.2 by 10 power 7 kN per meter square. Poisson ratio of concrete is 0.2. Unit weight of concrete is 25 kN per meter square, and shear modulus of concrete is 1.3 by 10 power 7 kN per meter square. The concrete sections are designed according to EC2 code for following parameters. Concrete grade is C30 and steel grade is 500. This tutorial manual will not present the theoretical background of modeling the problem. For more information concerning the method of analysis, a complete reference for numerical calculation methods is well documented in the user guides of ELPLA. After opening the program from file list, we will select a new project, and then from calculation method wizard we will select an S of slab floor, then next, and from system of symmetry we will select unsymmetrical system, then next, and from option we will select slab with girders, support, concrete design, then save the project to the destination folder, maybe 4, and save it. And then from project identification we here can enter title, date, and project name. Maybe the title analysis of web floor, and the project is floor, then save it, and then FENet data. Here we can select slab type. It will be a rectangular with 7-meter length and 6-meter width, then next, and from generation type we can select type of generation here, and we will select the first one as square type of FENet, then next, and from girder definition or grid definition, sorry, we will select here the interval, number of interval, and grid interval. It will be 1-meter interval, so we have 7 grid intervals in X direction and 6 intervals in Y direction, then finished. Here we have to delete some nodes to reach the required plan, so we will select the node, then remove nodes. Here we have, then save it and close. After that we will select slab properties. From slab properties we have to enter unit weight of slab material. It will be 25, no change here, okay. And for element groups we can enter each element properties. All slab properties have the same properties, with slab thickness 10 centimeter 0.1 meter, Poisson ratio 0.2, and Young's modulus 3.2 by 10 power 7. Then OK, and save and close. After that we have to select girders, and we will select girders group. Here we can select cross section definition. All girders have the same cross section. It will be a rectangular cross section. Okay, the Young's modulus will be 3.2 by 10 power 7, and shear modulus is 1.3 by 10 power 7, and the height of girders is 0.6 and width 0.15, and girder weight is 1.875. Then OK. After that we can add girders. For vertical girders we can add it from upper point to lower point. Here we have girder number. If we have different types of girders we can select it from here, and start node number, end node number, so we have to select OK. After that we can add other nodes, other girders, and then add horizontal girders from right to left. Then save and close girders. After that we have reinforcement. Here from design codes we can select the code we will use for design, and we will select the Aero code or EC2 with concrete C30 and steel 500. Then save it. For loads, first we will check option of snap from setting, and then float parameters. Here snap to node, and we already selected, so OK, and back to loads. From load we can use view group to view girder system, and then add distributed loads. For cantilever slab it will be 4.5 kilonewton per meter square, and for other area it will be 3.5 kilonewton per meter square. 3.5 and 3.5. Here we have data result. We can change the font from font setting font. We can change it to maybe 3. Save. OK. Maybe we can change it again to 4. Then save, and from load we can close it. After that we can add supports, and we can use view group again and select girder system, and then OK, and then we can select nodes, then add supports. For displacement, it will be 0 for all supports, and for rotation it will be F. We don't have to change it here. Then save and close. After that we will go to solver to solve the problems and select computation of all. And here is the summary of the computation, and check off solutions for load and reaction, and it's the same also for X moment and Y moment. It's the same for load and reaction, so it's stable. Okay, then we will go to result, and from result we can display or view data result as a plane or isometric view. For example, in plane we can select net numbering, element groups, system of loading, boundary condition, girder system, column type, slab thickness. Here's slab thickness, for example. We can change fonts of everything from setting and font of data and result, and we can save it. We also can change font of title for identification, box for legend, access list. Like again to isometric view, we can show the slab thickness as isometric view, or girder system. Here's the girder system. We can use view group to add supports and boundary condition here. Also we can use isometric view for that, and for result we can use contour line, isometric view, circular diagram, deformation, principal moments, support reaction, bunching shear if we use it, and beam results. For contour we have displacement, moment in X direction and Y direction, shear force and slab, top and bottom reinforcement. For example, displacement, here is that. We can add girders and supports, and we can use from setting display view to select which one to use. Load here. We can remove contour line, can remove result or display it. And for circular diagram we can use it maybe for support traction, and also we can see the deformation and result of beam in plane, and also isometric view. Here is it for isometric view, and result of bending moment in plane for beam. Here is it. Here we use to define the beam from right to left for horizontal beam. So we have bending moment, the positive bending moment here below the line, and negative is above the line of the beam. If we define it from left to right, we will have the same result, but the program will draw it in reverse direction. But in isometric view, it will be the same. Thanks.